the antiderivatives which we've solved so far have been ones that are considered basic antiderivatives. And the reason being is that we're taking our basic derivative rules and kind of going in reverse, all right? But if you notice, the one thing, or two things actually, that we really haven't touched upon with those basic antiderivatives are complex products and quotients, okay? So what's what I mean by this? If I ask you right now, what's the antiderivative of sine x? Okay, well, that's something that you're capable of solving for, capable of finding. Whether you have it memorized at this point or not, doesn't really make a difference, but we know that one way or another we can say that the antiderivative of sine x is going to be the opposite of the cosine of x plus c. Okay, that's just one that we know. Why? Well, because cosine derives to the opposite of sine. So the opposite of cosine will derive to sine, which is exactly what we see right there. Okay, and whether we are adding or subtracting doesn't matter. If we have the antiderivative of sine x minus cosine x, it's still not an issue. We just antiderive them one at a time. That's what our integral properties state. So we have the opposite of the cosine of x, and then minus the sine of x, because again the minus sign stays, and cosine's antiderivative is sine, and then the two arbitrary constants combine for 1, so we have a plus c. Okay, so either of those problems is no big issue. But now here's the question. How do we work with a product, something like sine squared of x times cosine of x dx? That's something that's much more complex. And we have to figure out a way to do it. We cannot, unfortunately, our properties do not allow us to separate a product into two parts like we can with a difference or a sum. If we have a product, we have to come up with another way. Right? So when asked often how do we deal with a product in an antiderivative, a lot of times students say, well, how about the product rule? Because we did a product rule when we were deriving, okay? And you recall what the product rule was, okay? So the product rule, if you remember, let's just use u and v, all right? U and v, all right? So that means that we're going to derive the first and keep the second, plus then we keep the first and derive the second. So we have u prime v plus v prime u. Okay, we derive each of them one at a time. Now remember, when we're doing an antiderivative, this is what we would be starting with, and our answer would be that. That's how the antiderivatives work. Well, we don't want to start with the sum of two products. We want to start with just one product. So the product rule doesn't really help us here, but the chain rule does. Because if you recall the chain rule's solution, the derivative, our final product when we use the chain rule, was a product, okay? If we think about it, the derivative, remember, let me go back to this, I'll go to Newton's, all right, we had f of g of x. All right, when we took the derivative of f of g of x, all right, we have an outer function f and an inner function g. So we derive the outer function, f prime, we keep the inner function, g of x, and then we multiply that by the derivative of the inner function. That was, it's kind of off the screen there, but that's g prime right there, and I apologize for that. That product was the answer. So if we're doing an antiderivative, then that'll work because we're starting with the product and we finish with a single function, which is a composite function. Okay? And that's our solution for coming up with how do we deal with anti-deriving a product, okay? We're going to try and identify what is that inner function, what is that g of x, because if we can work off of that, we're in good shape. Let me ask you another question, it's a little bit separate from that. If I asked you to do the antiderivative of x squared dx, could you do so? Absolutely. You know that right now this is x cubed over 3 plus c. So here's the deal. What we're going to try and do is bridge the gap here. We're going to try and turn sine squared x cosine x dx into something that is the equivalent of x squared dx. Okay, we're not going to use the same variable. We're going to use the letter u. That's why it's called u substitution. But if we perform the substitution correctly, we can turn a complex product into a much easier antiderivative, and then we can take the antiderivative of the easy thing. That's the idea behind the u substitution, as the following videos are going to show.